Good morning, or afternoon, or evening. I'm getting used to saying that for you guys. Whenever it is that you're listening or watching this little video lesson, I hope that you guys are having a great week. We're getting towards the end. We've got one more week next week, and then we've got a day off for Memorial Day, and then we've got that final week for exams. So those of you freshmen, this is going to be new to you, and for you 8th graders as well. This exam week at the end, well, maybe it won't be too different because you guys usually have end of the year exams. So anyways, I'm talking myself in circles. We've kind of made it to the end of everything we want to talk about with probability for the semester, really. And so just to wrap things up, we've done pretty much, we actually have done all of our assignments in Delta Math for probability, but there's some terms and concepts in the textbook that, since we didn't go through the textbook for this last unit, I'd just love to touch on a couple of the key terms there that are super important. So the first one, I guess I should probably just mention it since it is right on the screen, but the probability of an event happening is always going to be the number of successful outcomes divided by the number of possible outcomes. So like, let's say I said, what's the probability that I am going to, how about let's use it applicably. What's the probability that Mr. Dealman is going to have is going to be allowed to have all of the guests that he invited to his wedding actually be able to attend? Well, it's a little bit more complicated of a situation because it's not necessarily chance, right? But there is probability there. Like, what's the likelihood? Well, if I was looking for a percentage, I would do the number of successful outcomes divided by the number of possible outcomes. I'll use a more hands-on example. Let's say I'm rolling a dice, right? And let's say I really want to roll a 4. What's the probability of me rolling a 4? Well, the number of successful outcomes I'm only regarding is 1. In the number of possible outcomes, well, there's 6 sides to each die, so there's 6. So the probability of getting a 4 when I roll the die is going to be 1 divided by 6. Pretty straightforward. You're probably like, Dealman, this is a snooze fest. I already know what I'm doing. So let's move on. A more streamlined definition, or I guess you could say, actually I'm going to just do a new page. A new very general definition is this word sample space. In sample space, it's defined as being a list of all possible outcomes. So rolling a die, when I'm rolling 2 dice, there are 36 possible outcomes, or pairings or combinations of the 2 dice that we could get. If I was just rolling 1 dice, I would have 6 possible outcomes. So my sample space, if I'm rolling 1 dice, would be my sample space, jumped ahead, would be 6, because there are 6 possible outcomes. Alright, so that's sample space. If I tell you that 2 events, right? 2 events are equally likely, so this word equally it means exactly as it sounds. It means that each outcome has the same probability. If you aren't taking notes, I would pause or rewind and kind of just make sure you're getting these things jotted down onto a sheet of paper so that you have it, that muscle memory, right? Putting it from the video to the pencil to the paper, right? All that connection that's going on there is really going to help you solidify these ideas into your mind, even if we're not going to specifically apply them and be assessed on them. But when you see these words, it'll be more recognition later on, like next year when you have to talk about these things again. So, anyways, equally likely. Each outcome has the same probability. If I said I wanted to roll a dice, if I wanted to get a 1 or a 6, these are equally likely. I wrote that word really wrong. Equally. Those are equally likely, right? If I roll a dice, I don't know how to say it ever. I apologize. If I roll a dice, if I want to get a 1, and let's say I'm playing with a buddy of mine and they want to get a 6, the likelihood or the probability of both of us getting what we want is going to be the same. It's going to be 1 out of 6. Now, it'll probably change if we were looking for, like, maybe we wanted them to add up. If we were rolling 2 die and we wanted them to add up to something, that would complicate it a little bit more. But we're not there. All right, next term, a probability distribution. A probability distribution is a description of all possible numerical outcomes of a random situation. So I'm going to insert, sorry, I had something go wrong with my audio there. I had to pause. I'm going to insert a picture of the table from the textbook, which I have now, which probably magically appeared for you, but this is the probability distribution for the sum of 2 dice. So if I roll 2 dice, what's the probability of me getting a sum of 2, or 3, or 4, etc., all the way up to 12, right? Because the highest our dice go up to is 6 and 6. So, what's the probability? I'll just fill out a couple of these, for example. What's the probability of getting a sum of 2? Well, if I'm rolling 2 dice, the only way that I can get 2 is 1 and 1 or 2 and 0. 0 is no such thing on this dice. So the probability of, in this case, getting a sum of 2, well, first, there's a compound probability here. The probability of rolling a 1 is 1 out of 6, and then the probability of getting another 1 is also 1 out of 6, and you got to multiply that, and that's 1 out of 36. So 1 out of 36 is that probability. Now, what about the, in this case, rolling a sum of 3? Well, that's a probability of, in this case, there are 2 potential pairs here. There's obviously the probability of getting, in this case, if I were to roll a 1 and to roll a 2, because 1 plus 2 is 3. Again, if I'm trying to roll 2 dice and I want them to exactly land on certain numbers, I got to multiply these probabilities to get their actual probability. So in this case, it's a 1 out of 36 chance that the first dice I roll is a 1 and the second one I roll is a 2. What if I switch that though? What if the first one gets a 2, that's a 1 out of 6 chance, and the second one gets a 1? Well, that's also going to be a 1 out of 36. So if I add them together, I get 2 out of 36. So 2 out of 36 chance. Now I could keep going with the 4, right? Obviously with the 4, I could do 1 and 3. So 1 plus 3, and then 3 plus 1. And then also 2 plus 2. Now there's no reversing there. So how many do I have? I got 1, 2, 3. And now we've kind of learned by now we're always going to have a denominator of 36 because we're trying to find the probability of one dice rolling this, a certain number, and another dice rolling the other number. So in this case, this is going to be 3 out of 36, etc. And this would go on and on and on. And once I fill this entire thing up in its entirety, that would be my probability distribution, displaying all possible outcomes for a random situation. Feel free to pause, ask questions, rewind if you need to for this particular definition. All right, so there's probability distribution, and then the next term, in this case, is actually going to be our final one, and it is the definition mutually exclusive or disjoint. So mutually, I always say that word, mutually exclusive or disjoint. They mean the same thing and are used quite commonly. Both of them are used quite commonly in math land. So, mutually exclusive. What do you think of when you hear the word exclusive? For me, I always jump to, this was never a term used when I was in high school, but it was always joked about as an older term. But saying like for example, my fiance is named Sarah. Sarah and I were dating our senior year in high school. So the term would be Sarah and Evan are exclusive, meaning they don't date other people, they only date each other. So that's what always jumps to my mind for exclusive, right? They can't be dating other people at the same time as them dating each other. That's what exclusive means. So, mutually exclusive or disjoint regarding probability is if got the grammar wrong here. So we would say that two events are, I'm going to say mutually exclusive. That's my abbreviation. If it is impossible for both events to occur on the same outcome. So, for example, if you roll one dice, you can't roll one dice and get a 1 and a 6. You're only able to roll a single dice and get one single number. Now, that's a little bit of a very, that's one very, 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 very extreme example in that case. But, for example, what if you were to roll a sum of 7 with a pair of dice and you get doubles on the same roll, right? So if I were to roll 2 dice and I get a sum of 7 and doubles, we would say that these are mutually exclusive events if they can't happen at the same time. Now, when you're rolling a dice, in this case, why would this or would this not be a mutually exclusive event? Well, getting a sum of 7 requires 2 plus 5, or 1 plus 6, or 3 plus 4, or going backwards, 4 plus 3, 6 plus 1, 5 plus 2. Are any of these outcomes, or any of these combinations, doubles? Answer should be no. Also, if you think about it, if you're doubling a number, you're always going to end up with an even number in return. If I double 1, I get 2. If I double 2, I get 4. If I double 3, I get 6. If I double 4, I get 8. If I double 5, I get 10. And if I double 6, I get 12. So there's no possible way for us to have doubles and get an odd number as the sum. So in this case, we would say yes. The probability of getting a sum of 7 when you roll 2 dice and doubles would be mutually exclusive events. These events cannot occur at the same time. Let me know if you have any questions. Obviously not live, but go to the Google Doc and let me know what questions you have. So I want to finish off by including and looking at one picture or diagram and just consider how we could represent what a mutually exclusive / disjoint event or events would be. Alright, so I think I should be good to go here. So, looking at this Venn diagram, event A is represented by the sample space, or the blue circle on the left, and the probability of event B happening is represented by the sample space of the green circle. Now, we know that in this case, events A and B are mutually exclusive, meaning they cannot occur at the same time. We know from experience that a Venn diagram represents option A occurring, option B occurring, or where they overlap, where they both could occur. We don't want overlap. Some of you might have already jumped right to that and said, oh, I know exactly which of these Venn diagrams represents a mutually exclusive event, or two mutually exclusive events. In this case, we definitely would not like the first one, because that overlap represents that event A and event B are happening succinctly together at the same time, the same outcome. And that's not what mutually exclusive means. It does, however, work out, actually just had an idea. It does actually work out for the image on the right, the Venn diagram, where event A and event B are their own circles and they don't overlap in any way. So that means that you can only be standing in circle A or only in circle B. There's no way for you to stand in both, because the space between A and B is actually a mile long. It's just not drawn to scale, because I know some of you guys would probably come back with, well, I could just put 1 foot in each. I caught you. So, anywho, in this case, the Venn diagram that represents two mutually exclusive events would be two circles that are not overlapping in any way, shape, or kind. So, we've gone through, in this case, the probability of an event. What does that definition mean? That's pretty basic, streamlined. And when I say that, I mean that you guys have already been working with probability, so that's not anything you haven't seen yet. We talked about sample space, right? It's a list of all possible outcomes. Equally likely events is the fact that each outcome has the same probability. Probability distribution is a table, really, that displays all the probabilities of your specific situation. And if I were to scroll up, probability distribution, it's a description of all possible numerical outcomes of a random situation. And then we got to mutually exclusive or disjoint, which means that two events are mutually exclusive if it is impossible for both events to occur on the same outcome. And we took a look at these two Venn diagrams. But I want to look at one final two final items to go over. And they are just the symbolic notation most commonly associated with probability. And I just want to explain what they mean. So the first one is the probability of, in this case, A and B. And in the textbook they say, what's the probability of A and B occurring? Well, we always write it in this symbolic notation where I've got P, which stands for probability, and then in parentheses you would say, well, A represents event A, and B means what's the probability that these two events occur at the same time? Well, if they are mutually exclusive, we know that that is equal to 0, right? The probability of two mutually exclusive events occurring at the same time, right, A and B, that's not possible at all. What if we switched it over to the probability of A or B? Does that change it up a little bit? Well, it does. Now this is hypothetical, so I'm not going to put a number or a decimal here or a fraction for the probability, but there is a way that I would always calculate this, right? What if I was saying the probability of rolling a 1 or a 4? Well, probability of rolling a 1 is 1 out of 6. The probability of rolling a 4 is 1 out of 6. So if I get either or, right, my odds go up when I say or. What if I said, what's the probability that I get 1, 2, 3, 4, or 5? Well, the probability that let's say I'm betting against a friend and saying, I bet you a quarter that I get your quarter if I roll this dice and I get 1, 2, 3, 4, or 5, but if it rolls a 6, you get my quarter. Obviously, the odds are stacked against your friend. You have the odds in your favor. Well, that's because every single time you say or, you're adding them together. So it's really going to be 1 over 6 plus 1 over 6, and that is 2 over 6, or simplified to 1/3. So in this case, the probability of A or B occurring is we're adding the probability of A to the probability of B. Probability, the likelihood, that increases when we say or in between two events. You say and, right, you're just making it more and more rare, more and more specific. But if you say or, it's almost like you're offering more options. Alright, so I think that will conclude this video lesson. This concludes our probability. There's more in the textbook, but if I were to show you a schedule of the past with Core 1, there's so many good things in the textbook, and it's a shame that we can't get through them all. But Chapter 8 typically is not finished in its entirety. And this year, we had a bit of a hiccup, right? Last 2 months, we've been online schooling. It's literally been 2 months from today since we started, or since it was announced that we would be doing online schooling. We thought it was only for 2 weeks, but we found out that it is, or maybe it was only going to be 3 weeks, but anywho, in any case, here we are at the end of the year, and we're doing just fine. So thanks guys for tuning in, and I will talk to you later.